Okay, so hi everybody. So I'm Jimmy. We're talking about a little bit more about Swift. Continuing on with it about the that portion of it, guano and nitrates. So quick background information. We talked about this earlier today, but 1708, 17A, counterpart to GW 1708 with 17A. So coincidence year B, but the big surprise was how incredibly underluminescent it was. It was like 2 or 3 orders of magnitude, like least less luminous than any other known short GRB. So kind of what's the cause of that? Why is it so underluminous? Detailed modeling of the afterglow shows it was definitely an off-axis structured jet. What exactly the prompt emission was, we're still unsure. So as stated earlier, but what it did show is we can see prompt emission from off-axis GRBs. That means we can potentially have a lot more counterparts in prompt GRB-like emission to gravitational waves. So with that known, let's take a quick look at our sensitivity landscape here. So of course, 1708 and 17A was a lot dimmer than a normal short GRB, even though we can detect more off-axis ones. So let's look at our detection horizon for a burst like that with our 2 GRB monitors that have been up there for a while, GBM and Swift-BAT. So this is how far they can detect 1708, 17A as a function of how much solid angle we could do that at. So GBM's about here, BAT's about here, and then the sensitivity of our gravitational wave detectors are way up here, showing we're missing a whole lot of parameter space. And really what we should be looking at is, is detection volumes that are rising because this is proportional to number of detections we get. And here, switching to a logarithmic scale, we are potentially missing out on a whole lot of parameter space where we can potentially detect counterparts and have a prompt, better localization than gravitational waves can. So that motivates greatly having more sensitive analyses than is currently done on board. So how to do that? First step is to actually get the data down that we need to do that more sensitive analysis with. So that's where Guano comes into play. The gamma ray archiver for novel opportunities. What this does is usually that time tagged event data or the full resolution data product is not always saved. Only when there's a GRB detected on board is it really saved. So this allows for on command of a prompt alert. We're able to send up a command through continuous commanding to be able to tell the spacecraft to save that data and bring it down next time you're doing next time we have a pass. So this enables us to actually be able to do the most sensitive analyses that we can on the ground, as opposed to just being able to do it on the spacecraft. So this allows for these sensitive searches, and then including better imaging, doing stuff during slews. Of course, better analyses, which I'll talk about here. This started back in 2003, and since then we've been dumping data for externally detected GRBs, gravitational waves, minor neutrinos, FRBs, and mostly from the external generated GRBs, we've added dozens of Archimedes localized GRBs to what Swift's done on board over the course of a few years. So go to those, talking about those better analyses. Let's take a quick aside to actually what BAT is. BAT is a coded mask imager. What this means is it has this kind of like large mask here that's half covered in lead tiles, a meter above this detector array of about 32,000 detectors. What this does is as light comes in, gamma rays come in, which you can't really, focus. They come in and create a certain pattern, a shadow pattern onto the detector plane using a cross correlation technique with the known mask pattern and the detector array pattern of your detected counts. You can recreate, what you see on the sky, create a sky image, and find a source inside of there down to about a few arc minutes. And this is what Swift does on board really well, over 1,000 GRBs like that. But how can we do better? So given that we have the data from Guano here, now we have what's called nitrates. You farm guano for nitrates, so that's where we got the name from. So using, pretty much with that data, we do now a likelihood-based technique where we do a forward-forwarding model and a lot of details going into this. But pretty much the sum of it is that we can do GRB searches to a much more sensitive amount. Statistics are handled better and everything like that. But the main sensitivity gain you get from is pretty much this large gain in effective area. By not doing imaging, you pay an efficiency penalty. Here, you don't transform the data; you keep it, in its original form, and you get a huge bump in effective area, and you get a lot more sensitive. At the cost of computational cost, but we got plenty of that down on the ground. So going back to our sensitivity landscape. Now this was our previous onboard curve, and now here's nitrates. on the ground. You get a huge boost here at our most sensitive region. We probe 3.5 times more volume and overall integrated across the entire sky. And nitrates now also extends outside the coded field of view without the limits of imaging. And now we get a 5 times overall through the sky increase in what our detection rate should be of 1708 light bursts. And we really go into this full parameter space here that, we're missing. Of course, nowhere close to covering everything, but, we're really delving a lot more into it. And then, of course, GBM has also their own on-the-ground targeted search that they've increased their own sensitivity to. So that's all about detection. So let's talk about localization. This is a likelihood-based analysis. We do inference to make localizations across the sky. So best case scenario, just like imaging can do, even to a lower flux level, we can still localize things down to about a 3 arc-minute circle. But say we can detect something just barely, but we don't quite have enough information to localize it to a single point in the sky. Let's look at kind of what our worst case scenario would be like if we do inference across the entire sky, we get this whole big mess. So looking at like a tiny fraction of a light curve of a above threshold detected GRB, making it really, really dim, and trying to do this inference across the sky, we get this. So here's the coded field of view, or like 15% of the sky here. And across it, this is the 90% contour of these yellow things, but those are little islands of probability where we zoom in and we see this oscillation kind of like up and down between peaks and valleys of about the full width half max of an instrument, which is about 1/3 of a degree. So you get across the coded field of view, all these tiny little islands of probability. And across outside the coded field of view, you get these where we don't have a quickly changing response, these large swabs of probability out there. So across the entire sky, our 50% area is 600 square degrees, 90% area is about a little under 6,000 square degrees. So it's not the entire sky. And, this is the worst case scenario. And it pretty much a full spectrum from that 3 arc-minute circle, to this. And now, what can you do with this? This on its own, maybe not really easy to follow up. So say if we had 170817A in the coded field of view, way out 90 megaparsecs. So about near our detection horizon, we would detect something kind of like that previous sky map. So let's say we took what the 2 detector sky map was for 170817, 50% area of about 50 square degrees, 90% about 200 square degrees. And we rotate the previous GRB and combine the sky maps. The result is pretty much you take a LIGO banana and involve it with a bunch of islands and you get this archipelago, which is a lot smaller. Here, pretty much 50% areas that pretty much just that point where the actual source is, and 90% area is just over a square degree. Something that's a lot easier to follow up than either the nitrates or the gravitational wave map on their own. And things, this would be available a few hours after they trigger and be able to just point your telescopes at these few islands. Which would be the true case if we get another BNS merger. And of course, like I said, this also extends out to outside the coded field of view. And for the best cases, we are able to have Fermi GBM type localizations where we have these kind of like 160 square degrees, 90% errors circles here. So we are now making these sky maps and sending them out to the world through GCN Kafka alerts. So, feel free to subscribe here and listen to these, and they'll be sent out, more information is found there. And then also the LVK is ingesting these alerts because we're following up every single gravitational alert above threshold or sub-threshold. So if anything combined joint false alarm rate, meets their public threshold, they'll send out a joint alert through the LVK alerts, having saying it's a quink alert, a coincident alert, and also that they'll have the combined sky map between the 2 sky maps themselves. So watch out for those. Okay, so how to actually find this data. I was supposed to talk about kind of just like tools and stuff and over there. So let's get to that part. How to find the GUANO data itself. So there's the GUANO webpage here, which lists all the GUANO triggers that we've dumped data for and the observation ID for it. So if you're familiar with Swift data, you can go on the archive or the quick look. If it's new data, go get that. Or, which was mentioned before, is the new API for the Swift tools written by Jamie and I believe Phil too, to be able to actually query and fetch this GUANO data or even your other Swift data. So definitely feel free to get that API. Makes things a lot easier to be able to grab whatever data you want. How to find nitrates results. So we have this webpage here where we list all the triggers from GUANO, and then most of them have had nitrates results. So go to this webpage. This will bring you to a whole list of triggers. Click on one of them, and you get the trigger report page. It'll look something like this. You have basic things like our rates light curve. You'll see things like the field of view where it was in the sky. And then along with the actual nitrates products themselves, you'll see a live recording as the analysis runs over a couple hours. And then at the end, you'll see the final sky map that's put out. Like I was saying here, here's a recent example of a GECAM trigger, an out of field of view localization we have there. And you'll have a link you can grab the sky map at, and also a figure plotted of what it looks like here. Then of course, we've got some documentation, which is, this is all new and messy, and feedback is definitely welcome, and excuse any messy in SGC, but definitely feel free to visit and find out all the necessary information there. So tools to actually analyze bat data. We have the 20-year-olds, old going back, standard tools, HESOF F tools that you can download and do the standard bat analysis. And also, find some analysis help here. There's a new great Python package written by Tyler Parsatan that is great for called bat analysis. That's great for analyzing our survey data, which is over long exposures. So pretty much for the bat survey, over months and months and years of data, you can do alternative exposures from 5 minutes to days to weeks and stuff like that. Do your own analysis with this. And there's now beta support also for TTE data from Guano or other event sources, where you can actually do finer scale analyses like GRB search timescales. And then of course nitrates itself, we have a pip installable Python package to be found here. Of course, this is very difficult to run. The first step of running it is downloading 0.5 terabyte of response files. So if you have a cluster and a lot of storage, definitely feel free to use this and try if you want. It takes about a few hundred core hours to run each search. But what we want to be able to do though is make this accessible to people. So you feel free to do this if you want, but I'm very much open to suggestions on how to make this more user friendly and everything. And I'm working on more efficient versions that would maybe not use the TTE data, use its continuous rate products that just has summed along all the detectors, and use the nitrates responses and make this a lot more approachable. You don't get localizations, but you still get a sense of analysis and can output sensitive upper limits and stuff like that. So if you have ideas of what you want to see coming out of that, definitely let me know. I'm here to tell my summary. So we can detect off-axis GRBs. We need more sensitive searches. Guano, nitrates joined together, provides that. Listen for alerts, and feel free to check out our live results here for nitrates results and our documentation on how to receive and use those probability sky maps. And also again, feel free to contact us. We have plenty of open projects. And if you want to just help with using the data or anything like that, definitely let us know. Thanks.